Hello viewers and welcome to another episode of Space Science with Python. Today we will talk a little bit about observational bias, and we will use again our comet database that has now an extensive size. We have now the tisserand parameter in there. We analyze the tisserand parameter and also other values and measurements, and today we will focus on a new parameter that is called the absolute magnitude. Now, before we start talking about the absolute magnitude, let's have a look. Let's have a look at the comet Leonard that is currently visible in the evening sky. So here's a picture of Leonard. Here's I think it's a picture from the 12th of December from Astronomy Picture of the Day. So quite a nice site where you get every day a new updated image of any astronomical topic. And here you see the comet Leonard with the star cluster M13. And the attributes or the characteristics of a comet you can see here is this tail. So mostly comets have two tails, a dust and an ion tail. I will not dive into detail into this, what's the difference. We have here something like a spherical region that's called the coma, and it can have a diameter of hundreds, thousands of kilometers or even millions of kilometers. And in there you have the small core. The core is now like the actual body, the solid, dirty ice ball where all the dust and ice and so on is evaporating from. Now, maybe you remember some images from Churyumov-Gerasimenko. It was sometimes described as a rubber duck or something. So it was like a binary object combined. And this is the core part in there. Now we don't see it here in the image. It's now really, really small, like a few kilometers. And talking about the size, we cannot really compute or determine the size of an object directly, but indirectly. And this indirect parameter is called the absolute magnitude. So if you recall, all the stars you see here, they have a certain brightness. The brightness is given in magnitudes, and also here recall a larger number corresponds to a fainter object. So a star with a magnitude of 10 is fainter than a star with a magnitude of 5 or 4. And the human eye can, I think has a range up to 6, magnitude of 6 or 6.5 under clear sky conditions, of course, with no light pollution. And of course, the magnitude of such an object like the comet varies, with the distance to the Earth, with the activity and so on. But there are normalized magnitude values, and this normalized value is called absolute magnitude. We have also an absolute magnitude definition for stars, for asteroids, and so on. And I don't want to go too much into detail about the equation. We will get to this in the future. And the most important thing is that the magnitude correlates with the size or with the diameter of the object. It's some empirical equation. And here it's like, similar link, a larger absolute magnitude, so the number becomes larger, corresponds to a smaller object. So a comet with an absolute magnitude of 10 is smaller than an object or a comet with an absolute magnitude of 5. So this is really important or simple to remember. Large magnitude, smaller object. And today we will take the Minor Planet Center database we already downloaded to dive a little bit, explore a little bit the absolute magnitude, and let's see if we can see some strange effects or biases. Of course, the title of the videos, I maybe should learn to write less clear titles. Spoils, of course, the results. We will get to a point where we see a particular bias in there, but we can approach this a little bit from a explorative perspective. So what we are going to do is we would like to extract some information from the database. Here, the very first cell imports some modules. Here we are connecting to the Minor Planets, to our comet database with the data from the Minor Planet Center. And now we use pandas to select some information from the database. We are going to take the perihelion in AU, and the absolute magnitude that's also in the database from comets underscore main, where, yeah, and let's maybe focus again only to objects with an eccentricity smaller than 1, so objects that appear regularly in the solar system or visit us regularly. So where was I? Where eccentricity smaller 1. And of course we need to take the connector. Let's see. Of course I have to run the first cell. And now it works. Let's have a look at the comets. So there's no name, no designation. We have simply the perihelion and the absolute magnitude here. And in total we have 840 entries. Now I would say let's describe the data a little bit, right? I mean, we can use the comet's df and then the absolute magnitude to get a better understanding or a feeling what's in there. So this is what you always do when you start to get some data. You have a look at the tabular format of the data. You may use the describe functions to get some insights. Yeah, 840 comets. The mean is at 12.5 mag, so a magnitude of 12.5. The median is around 13. So yeah, this indicates that the distribution is almost symmetrical, but almost. The faintest object has a magnitude of 22 and the brightest has -2. Yeah, if you would like to have some more exercise, just try to determine which object or objects have a magnitude of -2. So you can go to the NASA website or Wikipedia to check what these comets are. Now what we can do is we could, in the very first approach, I know last time you remember the kernel density estimator, but let's do it quick and dirty. We will use a histogram. So let's define a bin range from -2 to 22 in second bin steps. Yeah, so in total like 11 bins. So it's even a little bit undersampled for 840 comets, but again, it's not now. You're not creating any graphs or something for the for a paper. It's just for us to get a little bit an insight, and this plot will not be our main concern. Again, as always, let's create some let's create a dark background image. I like it. It's not everyone's favorite, but I'm a fan of it. And let's also increase the font size, font.size to 14. And now we can create a figure where we are plotting the absolute magnitude. Yeah, I know we also extracted the perihelion, but yeah, just wait until the end of the video. You will see why we will need this for our interpretation. Now we created our figure and axis, and we can create a histogram now. So we can say comets underscore df. A little bit clumsy today with the keyboard. Absolute magnitude. There you go. And then we say the bins equal to the bins range. Bins range. Yeah, let's use my favorite color. I like orange. Let's have some control about it. And also a little bit transparency so it will not burn in our eyes. Alpha. And then of course we have to set a label. So set X label. And this says simply the absolute magnitude. And the Y label is of course the number of comets because we didn't normalize anything. So simply number of comets. You can also set a title, indicating that we have an eccentricity smaller than 1 or so. You can also add a grid. Both axes. Line style, I prefer to use a dashed one because the frame is already solid. So it looks a little bit more decent, but well, again, it's preference and also a smaller alpha value, so it's not so dominant. Let's check. Invalid syntax because I used the dot and this is wrong. And there you go. Yeah, it's almost symmetrical. I mean, should use kernel density estimator. We see we have a few objects that are huge or large with a few kilometers of size or dozens of kilometers. And then we have more, so the smaller the objects get, more objects we have. But at a particular point, we have a maximum and then it decreases again strongly. Yeah, from around 15 meg to 20, whoop, you see a decrease. The slope is also way more steeper than before. So we have only a few objects that are smaller than for 15 meg. And okay, one could say, yeah, this is how the solar system is built, right? I mean, there are smaller objects, period. But is it that simple? I mean, why should be the border at 15 magnitudes? And if we take, for example, simulations, there's different simulations for cosmic dust, for asteroids, other minor objects. And they always say, well, the distribution of these objects, of the size distribution, should follow some kind of power law. So we expect that smaller objects, they are more frequent than larger objects. So the bin from 20 to 22 should be way, way larger than here around 15 magnitudes. So what's going on? That's strange. And first of all, to see whether we can even fit a power law or so, let's go a little bit deeper into the data and adjust our plot a little bit more. So we're creating a histogram now, not using matplotlib, but let's use NumPy. And you will see in a moment why I'm doing this. I want to do the the caps lock names are really bad. I should have changed them. Magnitude. And we can also set our bins equals bins range. Yeah, so the histogram is now being created with NumPy histogram, where we have here the values for these bins edges. And well, of course, with this information, I could plot this graph here, but let's have a look at another distribution, the summed up histogram, so the cumulative histogram. And for this, we use also NumPy function, this one here, where we put the abs mag histogram in there, and then we can plot it. So we can again create our figure and axis and so on. Maybe let me copy paste it a little bit so I don't have to reinvent the wheel. And let's lose a scatter plot because we will get to this in a moment. Now, before we plot anything, maybe let's have a look at the data so that we understand how this looks like, how we would like to plot it. So maybe let me execute this part first and then the cumulative list. Yeah, so you see the number increases up to 840. The length is 12. And then we have also the bin's edges. So how does this look like? So these are the edges. So from -2 to 2 and so on and so forth. And what's the length here? 13. So we have to be careful. We have to start, we have to go until the almost last entry. So if we want to make a scatter plot, because we have 13 points on the x-axis defining the bin ranges, and for the y values we have the number of bins minus, or the number of edges minus ones. So in a scatter plot it will probably not work, but let's have a look. If I use bins edge and I use only everything until the very last one, and I add +1, then I have the center of each of these bins. Yeah, it's a little bit dirty trick, but that's fine. So for values between 10 and 12, we will set a scatter point at 11 magnitudes. And again, this is quick and dirty for our plot, but it's fine to get an understanding of the data, I would say. So let's copy paste it here. Our cumulative histogram will be there. As always, the orange plot. Maybe I should put this into a function, the coloring, because I'm using always the same. Kind of boring though, maybe. And we can also set the X and Y labels again. Maybe also with the grid. Let me copy paste it quickly. And now we don't have the absolute magnitude. We have the absolute magnitude, but we have the cumulative number of comets. Yeah, so you see it increases. And now we see here that, yeah, we have only a few larger ones. Then, yeah, the cumulative has here some kind of, yeah, constant slope, and then it decreases again. But what kind of fit could we use here? Now, I know a lot of people now, some of you may say, oh yes, let's use machine learning, some kind of function. It even reminds a little bit of a logistic regression, but yeah, okay, logistic regression is used for classification. Anyway, a lot of people would now say, I have thousands of ideas, I'll use this small neural network to fit the data. Yeah, let's not do an overkill. I mean, let's represent the data a little bit differently. I mean, I always suggest to think a little bit what one could do instead of, yeah, perform some overkill algorithm. And what I just did, I just copy pasted our plotting. Okay, fine. And now I'm setting not the X, the Y label, the Y scale. And I want to plot it logarithmically. So let's see how this works. And there you go. Now you see, yeah, there's again some kind of slope. But remember what I said. I said, from theory, we expect some kind of power law. So if we assume that we observed almost all larger comets like this, the first 5 bins, then the rest should be, yeah, being predicted by this power law that's maybe defined by the first points. So here we could fit the power law easily, but then it would differ from our power law. So what we can do, we can work in this logarithmic space or domain and perform a linear regression in the logarithmic domain on, let's say, the first 5 points, extrapolate it and see whether or how the linear regression differs from the rest of our points. And of course, remember, we are doing a linear regression in the logarithmic space. So if we transform it back, of course, it becomes some kind of power law. Now, how we can do this? Well, let's first of all say, I said, let's do it on the first 5 dots, right? So we will use bins edge, and we use only the very first 5 ones. Yeah, Python starts at 0. And the absolute magnitude plot, yes. Oh, no, is something like bins edge, what we did before, -1 +1. Okay, now we can create the cumulative histogram for the fit. Also, let's take the very 5 data points. And now we can perform a linear regression. And for this one, we use scikit-learn. And speaking of which, I think I just added it in the requirements.txt. There you go. So please, please don't forget to rebuild your remote container. Or if you're already in your notebooks, you can write !pip install scikit-learn, and then it will install automatically. But yeah, for me, the requirements are already satisfied. But if you just have to install something, you can do it in the cell. But don't forget to add this in the requirements.txt. Okay, so we import the linear model. Now we define it, linear model dot linear regression, no arguments, a simple fit on the data, so no black magic going on. Absolute magnitude dot underscore fit. For not numpy, for scikit-learn we have to reshape it. I will show you in a moment how it looks like. This is the format scikit-learn expects. We have to, the y values have to be logarithmic, so cumulative fit. And then we can say cumulative absolute magnitude prediction, yeah, would be the reg.predict absolute magnitude plot dot reshape -1, 1. So what happens, we are instantiating the linear regression here in line 7. We are performing a fit on the linear model here in line 9, and then we use the trained model to perform a prediction. So it's really simple linear regression. This is really no advanced machine learning whatsoever. We just use the machine learning library because it contains the linear model stuff. Now let's have a look here first at this reshape thingy. So our data here looks like, I should maybe run this. It looks like this, but we have to put it into a format for scikit-learn where every feature is in own dimension. So after performing a reshape, we have here an array with every feature in its individual list. So this is the format scikit-learn expects, but also other machine learning algorithms like also, libraries like, for example, Keras expect this as well, because here is a simple one-dimensional fit, but there are also 2, 3, 4, 5 dimensions, or we have more features, and then having a standardized representation or visualization of matrices and tensors, is the preferred way. We have now our prediction. So what we can do, we can again create our figure and axis, subplots, the figure size again, favorite values for my screen. And then we can say x.scatter absolute magnitude fit, cumulative fit. Let's put it in a different color so that you can differentiate between points that are being used for the fit and the ones that are not being used. So with some marker and maybe some size. And then we use the other scatter plot where we have the, absolute magnitude plot and the cumulative histogram, where we have here again tab dot orange and the marker. So let's see how it looks like. Yeah, you see here, these are the dots that are used for the fit, and the rest is now the rest of the values. I could also say for the plot I want to use from the 5th index to the end, but let's stick it like let's stay with this one here. Of course, you have to make it now in the logarithmic scale, but first let me add the fit here. So absolute magnitude plot. Let's use the, did I use the plot here? Yeah, I used the plot for the whole prediction. And then we say, okay, 10 to the power of cumulative prediction, because we computed it in the logarithmic space. White dashed maybe. Alpha also 0.7. We can reuse some stuff from here. I think everything, yeah. And where are we? Here are we. And let's press enter. Oh, no. I induced chaos, I think. Should be here. Yeah. And there you go. You see the power law fitted on the 5 dots. And you see small deviation here to this point, and the deviation gets bigger and bigger and bigger. So it appears that we have observed less smaller objects than larger ones. If we compare it to some kind of power law based on the larger objects we have observed. And this makes perfectly sense, right? I mean, smaller objects are fainter, so we need larger telescopes, higher exposure time, and it's maybe even not observational at all, so it's quite difficult. We have this kind of bias also in stellar astronomy. It's called the Malmquist bias that says that, well, if you wouldn't correct with some kind of observational bias, we could assume that our cosmic neighborhood consists only of large stars and not of smaller ones, or the smaller ones are underrepresentative. Yeah, it's quite simple because the larger ones are brighter and they are easier to detect. So it's apparently, and it's not a big surprise, that larger comets are way easier to observe and detect than smaller ones. And this may appear like a trivial bias. You will say, yeah, sure thing. I mean, come on, this is clear for me. But their data contain a lot of biases or bias effects, and you have always be aware of that. So this is quite simple, but there are more biases out there. Also, maybe if you do machine learning on some other data, images, whatsoever, if you, for example, create a classification image classifier separating between cats and dogs, and the dogs are only huskies, then the machine learning algorithm will only take the features of the huskies and think, this is how a dog looks like, cannot generalize it. And so this is another bias effect, right? There are also selection biases and whatsoever. And this one is really important for stellar astronomy, but also for space science here in the solar system. Now, if you recall, at the very beginning, I extracted the information perihelion. So what could we expect? I mean, if fainter objects, smaller objects and fainter ones, they are more difficult to observe, are we even able to observe faint or small comets with a large perihelion? Well, probably not, because a small object, or let's say a large comet, if it's a little bit more outside, I mean, activity of a comet starts at, I think, 5 or 6 AU. So before it's very, very dark and faint. So beyond 5 or 6 AU, we would expect to only observe the largest comet, the ones that are so huge that they don't need even maybe activity to be observable. And the fainter ones, the smaller ones, they are only present in the inner part of the solar system. So they have to cross this 5 AU barrier. They have come close to the Earth or even close to the sun to generate enough activity to become visible. So let's create a simple scatter plot where we are plotting the absolute magnitude versus the perihelion. And the size of the scatter will scale with the absolute magnitude as well to become more present. So let's do it. Let's create figure subplot again with a figure size of 12.8, surprisingly. Come on. And now we can create a comet. What do we call it? Comet size plot. So what I want to do is I want to take the absolute magnitude subtracted from the largest absolute magnitude. So it's like 20 minus 20. So that I can use it later for scaling. So it's some kind of anti-proportional sizing, like let's say the largest absolute magnitude was 20 or 22. So we subtract 22 from 22. So it's 0. Okay, a size of 0 will cause an error. So we have to add a 1. And if an object has a absolute magnitude of, let's say, 1 minus 22 is then minus 21. And then if we take the absolute value, it will have the size 21. So a smaller number will correspond to a larger number for our sizing. Yeah, let's code it, then you will maybe get the spirit. Absolute magnitude minus the maximum value minus 1, because otherwise we will get a size of 0, and this will cause an error in our scatter plot. So let's stay with this. And then we can say comet. First we can execute it. Yeah, it's now empty, but let's see what this comet size plot is. These are our rescaled values. And now we can maybe scale them a little bit. So I think 25 and 6 or 1 will be a little bit too large for our, will be too small, I think. I don't know. Let's maybe first create a scatter plot, and then I will maybe adjust it a little bit. So let's create first the comets df perihelion in AU. And on the y-axis we say, okay, the comets df absolute magnitude. We can say the points should be wide, and like maybe an alpha value, because we will get a lot of scatter points. Let's take a look first. I would suggest also to put the larger objects on top. So let's invert also the y-axis. Invert y-axis. No, I think need to call this. Okay, so this is the perihelion, this is the absolute magnitude. Larger objects are on top, smaller objects are here. Maybe we can now use this for sizing. Yeah, this is a little bit too small. Maybe let's scale it a little bit. Maybe by the maximum value and then times 100 or so. Ah, yeah, this looks nice. Okay, before we take a look at the plot, let me first finish the labels and so on to make it more prettier. X label perihelion. So I know it's very tempting to just plot anything and then take a look at this and say, ah, nice analytics, let's continue. I would suggest always to really be, take the discipline to write documentation, to comment your code. I mean, you see my GitHub repository, I comment everything except my own sandbox, but hey, it's a sandbox. But everything I try to explain or to show, so it becomes clear also for me in the future what I did, and also some kind of plot or animation whatsoever is way more difficult to understand and reproduce even for yourself in a few months, and then you have to redo everything. So I can only encourage you to take some time to create proper plots and documentation and comments. Anyway, let's take a look. What do we see? We have the perihelion in AU on the x-axis. Yeah, I could also now scale it, start it at 0, but yeah, anyway. And we have here the absolute magnitude ranging from 0 to 20 where 0 corresponds to a larger object and 20 corresponds to a smaller object. Perihelion at 1 AU means the closest approach of the comet with our Sun is at 1 AU, so the distance between Earth and Sun. And of course, anything that goes here is smaller, the comet gets closer and closer to the Sun, so you see quite small values. And here at 5 AU we have Jupiter, and at 10 AU we have Saturn, so it goes way out into the outer solar system. And what do we see? We see what we expected. Yeah, we see some kind of cloud where the smaller objects, the ones that corresponds to a larger absolute magnitude, they are gathering here on the left side with the smaller perihelion. So probably we even observed or discovered them when they reached the inner part of the solar system, because then they created an activity and became so bright that we could see them. But these objects here at 5 AU, 6, 7, they are not really active anymore. So it's really difficult to observe or discover a comet that is very small. Here we only have the larger ones, yeah, the ones that are going, that are not even crossing the orbit of Jupiter. And we observed or discovered them because they're so huge, have such a large size that with our telescopes and our techniques, we were able to detect them. And you see there is some kind of border here between perihelion and absolute magnitude. Here you can imagine a line a little bit. And well, what you could do, for example, is try to see when have these objects been discovered, to see whether this line moved a little bit from, let's say, from here to fainter objects and fainter objects. So it would be nice to see this distribution changing over time. Maybe some small task for you for next time to see how this behaves. A small summary and outlook, and not an outlook, just a summary. I mean, let's see what we'll do next time. Observational bias is hell. So there are biases at all are hell. We observe things, we have stuff in the database, and we can analyze them and everything, but sometimes it's not very apparent to us that this data is biased, that there's data missing, or that some kind of information is present that's not actually there because it results from our limited observation capabilities, of the techniques, of the nature of the topic, right? I mean, smaller objects are fainter and cannot be observed easily. So you have always to be aware of bias effects in the data. Doesn't matter if this is comet data, asteroid, images, audio files, whatsoever. Be always aware that you have observational bias effects, selection biases, and so on, because they can ruin your machine learning algorithm, your regression, your interpretation. So even if you interpret your data, you write your thesis or your report, and then at the end somebody says, yeah, did you consider the bias effect? Well, your entire work is trash, right? So take your time for some data exploration. I know it's very tempting always to create some scientific insights, to create some fancy algorithms to show something, yeah, with a nice benchmark or with some nice analysis. But be aware that simple data exploration is the key to start with the data. And you saw in the last couple of videos that even simple plots and algorithms can reveal huge scientific insights, but also can show severe observational biases. I hope you learned something today. As always, have fun coding. If you have any questions, leave a direct message to me here or on Twitter or Reddit. And see you next time.